Okay, in the last section we're going to do here for Chapter 3, we're going to be primarily discussing how do we solve equations involving logarithms and exponential functions. We have some pretty good ideas so far how to do that because we've actually done a fair amount of them at this point. But we're going to look at a couple of properties here to start out with, and then we're going to also discuss the method that we've previously used to solve, and then we'll kind of make a comparison and see which one we think is maybe better. And bottom line is, if we're solving an equation, one's not necessarily even better than the other because they both get the job done, and so therefore we might be able to choose at some point, which we do. So the properties here for exponential functions are if we have any exponential function with the same base, okay, whatever the two exponents are, in order for those two to be equal to each other, the exponents have to be equal to each other, or else it would not make sense. And if I had 3 to the third equals 3 to the fifth, and that wouldn't make sense because 3 doesn't equal 5. True? Right? And so this property, seems like it's probably just common sense at this point for us, but bottom line is we're going to see how do we use this property to solve exponential equations. Similarly, with logarithm functions, if we have log base b of u equals log base b of v, okay, that can only be true if u is equal to v. Okay, so if u is equal to v, okay, if that's true, then u would have to be equal to v in order to have that first sentence be true. Okay. All right, so what we're going to look at then next is how do we use that property, the first property with the exponential functions, to solve this exponential equation. Okay, and again, there's more than one way to solve the exponential equation. We're going to do it with the one-to-one property first, and then we'll do it the other way second. Okay, so with the one-to-one property, what we want to have is a situation where we have something of the form b to the u equals b to the v. Okay? And so the thing we have to try to do is get the b's to be uncommon. We need the bases to be exactly the same. Okay? Because if we can do that, then we can equate the two variables, or the two exponents, and then hopefully solve that equation. So the first step we have to do, and this is going to be the same first step when we solve this the other way, is that we got to get this 40 out of there because we want to have something of the form b to the something. So having 40b to the something is not okay. We need that 40 gone. So what we're going to do is we're going to write 1/2 to the x over 2 equals 5 over 40. I'm just going to divide both sides by 40. And I'm going to go ahead and simplify that while I'm at it and get 1/8. Okay. All right. Questions so far? All right. Now the trick is to see if we can get both of these bases to be exactly the same. Because right now on this side we have 1/2 to the x over 2. On this side we have 1/8 to the 1. Okay. So this doesn't really do us any good because the b's are not the same. Our b here and our b here are two different things. So ultimately, if we're going to be able to solve this with this property, there's got to be a way that we can either rewrite this base or rewrite this base, okay, in terms of the same number. Now, if we think about 1/2 and 1/8, okay, there is a relationship, and we want to think of a power relationship. Okay, is there a power relationship between 1/2 and 1/8? I'll start out with this. Is there a power relationship between 2 and 8? If I go 2 to the some power, will it give me 8? Yeah, so conveniently, there is a relationship here. If there wasn't a relationship, then we would have to go solve it the other way, which I'm going to show you in a minute. Okay? So since there's a relationship here, what we need to recognize is that 1/8 is really just 1/2 to the third power. Because wouldn't that be 1/8 also, if I raised 1/2 to the third power? And so ultimately, what have I just done? Now I've put it in the form b to the u equals b to the v. Fair enough? Okay. And so if I can do that, and again, in all cases, we can't necessarily do that in every case. Okay. But if we can, then this can be solved pretty easily because at this point, that's just going to tell us that x over 2 equals 3. Okay. Because from that property, we said if b to the u equals b to the v, then u equals v. So there's my u equals v part. And I only got one more thing to do here to solve this, and that's to multiply by 2. And I could get the answer x equals 6. Okay, questions on that method? Now, as we know, there is more than one way to solve an equation, okay, in every case, because ultimately, if this is a calculator problem, or if we're solving this on the ACT test, do we need to remember how to do that? No. Okay. Because what can we do with the left and right sides of this and find an answer also? Yeah, graph them. Okay. If I graph this function and graph this function, I always remember we're looking for the bigger picture here. At very minimum, we should be able to find the answer to every equation we want to because we have a graphing calculator. Okay? So if we graph the left and graph the right, see when they intersect, guess where it's going to be? 6. Okay. All right. Now, 2 ways so far then. We got the one-to-one property way of solving this exponential equation. We have the graphing approach that we could use to solve it. And the other one is going to be what I showed you yesterday, where we use logarithms to solve it. Okay. When we have an exponential function in our equation and we want to get the x by itself, okay, another good method would be using logarithms. And the logarithm method is going to start out the same way. Okay, we want to get the b to the x, if you will. Okay, the variable, if it's an exponential equation, that means that the variable is in one of the exponents. And therefore we want to get the b to the u part, if you will, alone. That's going to be step 1. So if it's not alone, we're going to go ahead and get it alone. And then from there, what we want to do is we want to take the log of both sides. Now, you can take the log or you can take the natural log. And as I explained yesterday, which one should I choose? I would choose the natural log because why? It's one less letter every time you write it. Right? So no reason that you can't use log, but I generally use natural log. So I'd write natural log of 1/2 to the x over 2, natural log of 1/8. And what that allows me to do, okay, is take the exponent and put it out in front. So then my next step is going to be x over 2 ln of 1/2 equals ln of 1/8. Alright, and then from there, I would divide by ln of 1/2. And I'd be left with x over 2 equals, and I'm not going to put any decimals in here because I'm just going to calculate this all at the end. But with my steps here, I would have that on the right. And then of course from there, I would just get x alone by multiplying by 2. So if I take my 2 times ln of 1/8 over ln of 1/2, okay, that would be the exact form of the answer. Okay, if we calculate it, maybe it's a nice answer. We already know it's going to be a nice answer because we solved it the other way. But if I type it in as 2 ln of 1/8, divide that by ln 1/2, we get 6. All right. And so ultimately, which of those 2 ways is the better way to solve that? Okay. Neither. They're both just fine. You can use either method. One of the things that the one-to-one property relies on, though, is that you can actually write the 2 bases as the same number. Okay, and that may or may not be difficult, depending on what the numbers are like. Okay, this method, I like this method because is there any stipulation about knowing bases or comparing bases? No. Okay, this will work how many times out of 10? 10. Always. Okay, this always works. Okay, and it's always, to me, I personally feel like this is a simpler way to do it because of the fact that we don't have to worry about trying to compare bases and make one base into the other, etc. So I prefer this method myself. Okay, if you're asked to do it with the one-to-one method, then there's probably a pretty easy way to compare the bases. Okay? If it just says solve, I personally would choose this way. Okay. Okay. All right. Let's take a look at a couple other examples of solving. I want you to see a couple more here. On page 331, we're going to look at number 11 together. We have 1.06 to the x equals 4.1. Okay. So here would be an example of one where if I tried to compare these 2 bases with each other, am I going to be able to find a nice power of 1.06 that gets me to 4.1? Probably not. Okay. So the best method here then would be to recognize it's already of the form b to the u on one side. So I would go ahead and take the natural log of both sides, and that would allow me to write x ln of 1.06, ln of 4.1, and then at that point, the only thing we need to do is divide by ln of 1.06, and we'll have our x by itself. Okay. So by composing both sides with the natural log, allows us to take the exponent and put it out in front, which makes it a much easier equation to solve. So in our case, we'd have ln of 4.1, ln of 1.06, and from there we could divide those 2 with our calculator and get the final answer. Okay. Another one I want to look at on that same page is number 15. It says 3 plus 2e to the negative x equals 6. Okay, I chose this one to illustrate kind of like the previous problem that we did. We are not ready to use logarithms at this point because the b to the u part is not alone. Okay, like we had a 40 in front of that one, we had to divide by the 40 first. Same thing here. So we might have to use other equation solving techniques to get it ready to use logarithms. So if we go minus 3, that would leave us with 2e to the negative x equals 3. And people generally mess this up by doing logarithm right now. Okay, but it's still not of the form b to the u because there's a 2 out in front. Okay, the b here is our e, the u is our negative x. Okay, so still not ready to be solved because of the 2. So therefore we need to divide by 2. I'm going to take it over here and I'd have e to the negative x equals 3/2. Okay. Now it's ready to be solved. Okay, so the first thing we need to do is get the b to the u part by itself. Okay, and once we do that, if we take the natural log of both sides, in this particular case it's really very convenient because what do I know about the natural log of e? The natural log and e are inverses, therefore the answer to that is just the argument. Okay, I don't even need to bother bringing it out in front because I know that when I compose the natural log and e, which are inverses, we're going to get the argument left over. Okay, you can bring it out in front and recognize that it's negative x times ln e. And what is ln e? It's 1. Okay. And then ultimately we have over here ln of negative 3/2. And so exact answer wise, we'd have negative ln of 3/2 over here because we divide by negative 1 to get the x by itself. And if they wanted a decimal for it, we could certainly type that into the calculator and get an answer. Okay. Good. Questions so far on solving exponential equations? All right, the other part we're going to look at today is solving a logarithmic equation. And once again, I've shown you a method for solving a logarithm equation, and that entailed changing it to exponential form and then solving the result. Okay, we'll relook at that in just a minute. But I do want to look first at the method for using the common basis, the one-to-one property method. Okay, and what it boils down to is this. If we have a log sentence, okay, equaling some constant with an argument, whatever the argument may be. In this case, it's x cubed, so log of x cubed equals 3. And what we can do is we can rewrite the right side that has the constant on it as log 10 to the 3. Now, I want you to think about why that's okay to do. Okay, because what do we know about log 10 of 10? Okay, log 10 of 10 is 1. Okay, and so think about that. If I were to put the 3 out in front of here, and it was 3 times log 10 of 10, wouldn't it just be 3 still? Okay. So what we're going to do is we're going to take the right side, the constant side, if you will, and we're going to compose it with log 10 of, and then the constant becomes the argument here, becomes the power. Now, the reason we use log here is because we had log given on the left-hand side. If this was an ln sentence, then we would have used ln over here instead, or whatever base that we needed. Okay. Now, what this does for us then is recognize that these are both logs of the same base. Okay. So what do we know about both arguments? Both arguments have to be equal. Okay. And so hence we can say that x to the third equals 10 to the third. And what does that tell us about x? It's got to be 10. Okay. All right. Now, I want to solve that sentence the other way. So I'm going to write log x cubed equals 3. And I'm going to just put my little 10 down there, even though we don't have to have a 10 there, because we know it's implied to be there if we do that. Okay. And if I solve this the other way, and remember the other way is to change it to exponential form and then solve the resulting equation. I'm going to write it in exponential form by going base to the other side. Base to the other side equals argument. And notice what I got by doing that. Same exact result as I had in the previous one. And so 10 equals x, we can get it that way too. And again, which way is better? Neither. They're both valid ways to solve the equation. Okay. Ultimately, if it says solve, then you can pick whichever way you'd like. Okay. In this particular case, could we also use a graphing approach? Sure. We got log base 10, so we could graph that, and we could find the intersection as well. Okay. I do want to look at little more complicated logarithmic equation here.